Hi guys. Hey, today we're going to talk about Taylor's theorem, okay? And today is March 25th, 2020, okay? All right, so Taylor series right here. We have a Taylor series right here and it's centered. So I want to add this centered at, and what's it centered at? It's centered at x equals a. Okay, so we've talked about Taylor series the last couple lessons, okay? And so this is the Taylor series, you know, f prime over 1 factorial, right? And this is f of the zeroth derivative over 0 factorial and so on and so on and so on, okay? And this is the Taylor series in sigma notation, and we have to go forever for it to be the Taylor series, and for the function and the Taylor series to be the same, we have to go to infinity, right? Okay. So we're going to talk about today, like how, if we use a Taylor polynomial of order n, okay, how good of an approximation is it? Is there a way to figure out, is it a really good approximation? Is it not a very good approximation? And we're going to do all of that today, okay? And it's going to be, I'm going to tell you, today's going to be a lengthy lesson because at the very end, we're going to do some practice AP questions, okay? All right. So what I want to do is this, if we stop, okay, if we f of x is equal to all of this Taylor series, Taylor polynomial, right? And right from here to here, okay, would be, and we stop it. So I'm going to put it right there, okay? We would say f of x is approximately this Taylor polynomial of order n, right? So this is Taylor polynomial. It's a Taylor polynomial of order n. Okay, we could also say it's a Taylor polynomial of degree n, all right? So there's a bunch of stuff. If we stop it, we wouldn't be putting equals. We shouldn't be putting equals, okay? We should be putting an approximation if we stop it, because this polynomial and the function are, it's approximating the function. It's not exactly the function, okay? Now, if we add to this, okay, and I want to take these dots off, okay, and we add to this the remaining part, okay, this is called a Taylor polynomial. This other part is called the remainder, and we use r sub n of x, all right? So this is called the remainder. And that's the leftover part that we're not using to make the Taylor polynomial equal the function, okay? So then this would be, if this is Taylor polynomial of order n, we would say p sub n of x. So that's what this piece is, okay? So to help you understand what the heck I'm talking about right now, okay, we have f of x, that's the function, the actual function, like e to the x or one of those, okay, is equivalent to the Taylor polynomial of order n plus the remainder r sub n of x. So this is the exact function. Okay, we get the values, the exact values for the function. This right here is an approximation of the function. So approximation of the function. And I'm going to slide this up a little bit. And this part right here is the remainder. Okay, so how could we get how far different the polynomial is from the function? Okay, so this is an equation that would be true. Okay, so this would be, so the r sub n of x would be the n plus 1 derivative at a over n plus 1 factorial times x minus a to the n plus 1 power plus f, the n plus 2 derivative of f at a over n plus 2 factorial, and so on. It'd be all the rest of these that we're not writing, okay? That's what the remainder would be, okay? So to know what the error is, which is also called our remainder, okay? The error we could get by taking this Taylor polynomial of order n and subtracting it. So it would, and we would take the absolute value of it, okay? And so we'd say the absolute value of f of x minus the Taylor polynomial of order n at x. And what that would equal is the absolute value of r sub n of x. So really all it is the error, and errors is like how far off are you? So it's got to be positive. That's why we're using the absolute value, okay? Really all it is it's solving this equation, right? Because this is an equation. The function is exactly the Taylor polynomial plus the remainder part. If you move this over, the Taylor polynomial over, and you subtract them, you would get the remainder, or how much off you are. All right. Now, a lot of times, because of the absolute value, the order of how we subtract these really doesn't matter. Okay. Because if you take the absolute value of like a number 5 minus 3, that'd be the absolute value of 2, which is 2. But if you do the absolute value of 3 minus 5, that would be negative 2, but you're taking the absolute value. So it's also 2. The order doesn't matter. So a lot of times what we'll do is write the Taylor polynomial first. Okay. So what you're going to see on the next few pages, all right, is that the error, the way we're going to calculate error, how far off we are, is to take the absolute value of the Taylor polynomial of order n at x minus f of x, and that would also equal the absolute value of the remainder. Okay? And that's the first part of this lesson, okay? Okay, for this first example 1, okay, we're going to use graphs to find a Taylor polynomial p sub n of x, so the nth order Taylor polynomial for sine of x, so that the absolute value of the nth order Taylor polynomial minus sine of x, the absolute value of that, is less than 0.01 for every x in negative pi to pi. Okay, so basically what we're trying to do is we're going to get an approximation, okay, for sine of x using the Taylor polynomial, and we're going to look at different orders to see, all right, between negative pi and pi. I want the difference between the Taylor approximation and the Taylor polynomial approximation and sine of x to be less than 0.01. And I know this is a little bit confusing right now, and I get that, but you got to hang in there right now, and I'll walk you through this, okay? But what we want to do is I want this to happen between negative pi and pi. So to set up our graphing calculator, and I'm going to pull up the graphing calculator in just a minute, we're going to want to set our x min of our calculator to be negative pi, and then our x max to be pi, okay? And why? Because I want the left side of my screen to be negative pi, and I want the right side of my screen to be pi, because that's where I want this to happen. I want this to happen between negative pi and pi. X scale really doesn't matter in this problem, okay? I would probably make it be pi over 2 or pi over 4 or something like that, okay? I'm gonna make it pi over 2, all right? And then we're going to look at the output for the difference between the Taylor polynomial and sine of x, okay? And we want the output for that to be between, well, less than 0.01. Now, the smallest this could be is 0, all right? So we're going to want to set our y min equal to 0. And the biggest we want our y max to be is 0.01. Okay. Y scale really could be, it doesn't matter in this case. Maybe Y scale to be 0.01. 0, 1 maybe, okay? You could maybe do that. That way there'd be like 10 of them between 0 and 0.01. All right. We're going to let our y min, not our y min, I'm sorry, our y sub 1. We're going to let y1 equal sine of x. We're going to let y2 be our Taylor polynomial, so p sub n of x. And what we're going to do is we're going to do a first order Taylor polynomial, and then a third order Taylor polynomial, and a fifth order Taylor polynomial, and a seventh until we get to this thing that's less than 0.01, okay? And then we're going to have a y sub 3. Okay, so y sub 3 is going to be the absolute value of p sub n of x. So the nth order Taylor polynomial, okay, minus sine of x, okay? Now, what this is going to be is, this is y2, so we're going to type in y sub 2 minus, and sine x is going to be y sub 1, okay? Now, we're going to start, I'm going to start listing a couple of these, and then we're just going to see, okay? The first order Taylor polynomial for sine x would be x, all right? And then we don't have a second one because we don't have a second degree Taylor polynomial, okay? Because it goes, remember, it goes x and then minus x cubed over 3 factorial, okay? So this is where it's helpful to know that chart that I gave you, okay? So we don't have a p sub 2, but we have a p sub 3 of x, because p sub 3 of x would be x minus x cubed over 3 factorial, okay? So that's a third order Taylor polynomial for sine x. And then we don't have a fourth because we don't have a fourth degree polynomial, okay? So we have a fifth one, p sub 5 of x, and that would be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And then let's do p sub 7. Okay, and that would be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and then minus, and we don't have an x to the 6th. That's why we don't have a Taylor polynomial for this for order 6. Okay, we have just the odd one. Okay, so then this would be x to the 7th over 7 factorial, and then we'll look at, if we need to, we'll start with these, and then we'll come back and look at, do we need a 9th order, okay, to satisfy this condition, okay? All right. All right, so now with our graphing calculator, we want to press window, and we want the left side of our screen to be negative pi, so negative pi, and then our x max to be pi, and then our x scale to be pi over 2 or pi over 4. Remember I said that just a minute ago, okay? I'm going to do pi divided by 2. And then our y min, 0. And then our y max is going to be 0.01. You guys, on the notes, I just realized, no, we're okay. Never mind. Y scale is 0.001. All right. And then let's go to y. Okay. Let's clear this out. Okay. We want y1 to be sine of x. And at the very top, just make sure you're in radian mode. Okay. Because we'll definitely need that. I'm going to clear this out. This is from the other day. Y2. Okay, so we're going to do the first order Taylor polynomial first. Okay, so that's going to be x All right. And then let's just go ahead and graph that and see what the heck's going on right now. Okay. So graph that. Okay. And you don't really see anything, right? Okay. What we want to do, I'm going to go back. I wanted to see what that was going to look like. Okay. What we want to do is we want to find the absolute value of the difference between these. Okay. All right. So I'm going to go alpha window to pick up the absolute value function. So select number 1. And then I'm going to type in, and we want the nth order Taylor polynomial to be first. So that is my y sub 2. So alpha trace, and then number 2, y sub 2, and then minus, and then the sin x, the actual function. Okay, so you could type in sin x here, or you could type in y sub 1. So I'm going to type y sub 1. So y sub 1. Okay, and then I'm going to turn these off. So, and you go on top of the equals and you just press enter so the equals isn't highlighted, and what will happen is those won't be graphed. So what it is we're going to find the difference between the actual function and the Taylor polynomial, and we're going to do that, the difference between them, between negative pi and pi, because that's our x min to our x max. Okay, and let's go ahead and take a look at the graph of this. Okay, so if you look at this, all right, so this down here is 0, and this is the top of the screen right here where my cursor is 0.01. This side is negative pi, and this side is pi. So I want to see, what I'm looking for is for the Taylor polynomial to land somewhere in between here, because then, and over here, and it contains, the entire graph is contained in this window. Because what will happen then is that I know that since this top part is 0.01 and this is 0, I'll know that error is within 0.01. Okay, so right now there's no way, because this just keeps going up and up and up. Okay, all right, and we don't see it in between 0 and 0.01, and we don't see it between 0 and 0.01 for the entire function. Okay, so now let's go back to y equals. Let's add one more term to our Taylor polynomial. So this is going to be minus, and then alpha x to get our fraction bar, and it's going to be x to the third power over 3 factorial. So 3, and you could do 3 factorial, and it's 6, but I'm just going to do type in the 3 factorial. So 9. Okay, and now let's graph that. And you're starting, and what happened is it's graphing this one. So we don't want to graph this one. So go back and make sure. Every time we add a term, we're going to have to turn the equals off. Okay. You know, and I want to change the color. Let's make this one green. I don't want it to be black. I want it to be a different color. Let's make it orange. Yeah, orange. Let's make it green. Sorry, can't make up my mind. Okay, so now we graph it, and we can see, okay, so it's spread out a little bit more, right? But it's still not within 0. The entire graph needs to land between 0 and 0.01 for that difference to be less than 0.01. So let's add another term. So y equals, let's come down here. And then plus, and then alpha x, and then x to the 5th over 5 factorial. So 5 alpha window 9. Okay, and then again, let's go on top of the equals to turn it off. The only way I can do this there is hitting the arrow buttons. Okay, so let's graph this one. Okay. And a little bit better, right? A little bit better. Okay, let's add the 7th order Taylor polynomial. And that's going to be minus and alpha window x to the 7th over 7 factorial. And highlight that equals, and then let's graph it. Okay, so you're starting to see, okay, this is, we're looking at between negative pi and pi, okay, and it's starting to look like it might, we need this part right here to land in between here. So between negative pi and pi, the absolute value of the difference between the Taylor polynomial of order, in this case 7, and the function sine x, the difference between the absolute value of the difference between those needs to be within 0.01. So this bottom is 0, this top is 0.001. It's not within that tolerance yet, okay? So we're going to go back to y equals, all right, and come over here to the right. Okay, and then we're going to add the next term. So that's alpha x to get the fraction, and it's going to be x to the 9th over 9 factorial. And it's quicker to come down to the previous or the next line and then come back up to the equals, I think. You can just get there faster. Okay, so now let's press. Okay, so this is a 9th, a Taylor polynomial of order 9. Okay, and it's the approximation for sine x. So let's go ahead and graph. And there we go. Okay, let's check on the right hand side. Okay, so the difference between the 9th degree Taylor polynomial and the actual function sine x is now between 0 and 0.01 from negative pi to pi. So that entire interval from negative pi to pi, the difference between the two is 0.01. Okay? All right, so hopefully that's a demonstration of like this remainder and this error. Okay, this is a very visual way of saying that every x value between negative pi and pi is within 0.01 of the actual value. Okay, so if I put, let's say, I found sine of, let's say, pi over 3, okay? If I put pi over 3 into the Taylor polynomial, okay, I would be within 0.01. Why? Because pi over 3 is between 0 and pi, and I know I'm within the actual value and the approximated value. I would be within 0.01. Any value I pick between negative pi and pi, I would be within 0.01 of the actual value of the function. Okay, I think this is pretty cool to see this visually. When I was taking calculus, we didn't have the graphing calculators to even think about doing this, and so it's pretty interesting that we can visualize this. Okay, so now I'm going to go back to the paper. Okay, and we found our Taylor polynomial that will do this. Okay, all right. Okay, so from the graphing calculator, we now know that we had to go more than just the 7th degree, 7th order for this, okay? So we had to go to the 9th, right? So p sub 9 of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial, okay? And so find the Taylor polynomial for sine x where this tolerance, and let me slide it down a little bit, okay? So find a Taylor polynomial where this will happen, and we did that, right? And it turns out to be the 9th one, okay? All right? So, all right, we know that the absolute value of the 9th order Taylor polynomial of x minus, let me slide this up so you can see it. Okay, this is what I'm writing. So the absolute value of the ninth order Taylor polynomial of x minus sine of x is less than 0.014 every x in the closed interval negative pi to pi. All right, and that's how you solve this graphically, okay? Now we're going to talk about other ways to do this, okay? So let's go to the next, turn the page, and we'll go to the next example.